I'm Joonas Koivisto, and I'm also from Finland, as is told. And today I will talk about this nanoparticle measurements using handheld instruments. And there are many kind of handheld instruments like condensation particle counters, optical counters, and diffusion chargers. And today I will talk mainly about diffusion chargers, which measures lung deposited surface area. And I'll show what kind of lung deposited surface area concentrations we measured in different occupational settings. And then we use these concentrations to calculate inhaled lung deposit surface area concentrations. And those doses we compared with toxicological studies which are showing like this relation between polymorphonuclear neutrophilia and then surface area dose. And then we use these doses and dose responses to predict pulmonary inflammation risks. And then conclusions and future prospects in the end. But what is lung deposit surface area concentration? It's a surface area per unit volume, and it is defined as a surface area which is proportional to particle diameter to power 2. And we multiply this surface area with the particle deposition fraction in alveolar region. And this deposition fraction is proportional to inverse of particle diameter. So we get this kind of a unit which is proportional to particle diameter. So this is a basic concept of lung deposited surface area, or definition of lung deposited surface area. And we are lucky in this case because diffusion charger signal is also proportional to particle diameter. So it's kind of a lung deposited surface area monitor. And this is one kind of a surface area monitor, disc mini, which is handheld, and so on. And we use this disc mini to measure exposure levels in polypropylene injection molding, tungsten carbide cobalt fine powder production, and handling of nanodiamonds, fissure, manufacturing, and jet engine emissions. These are the scenarios which I show. And if we start from the polypropylene injection molding, it was an industrial site which were producing these car bumpers. And we used two different disc minis to measure from the injection mold site and then further away in packing area. And then in all cases we took also like microscopy samples and analyzed the particles, morphologies and compositions. So here is an example of like the concentrations what this lung or surface area monitor measures. So the primary signal is this surface area, and we can see that here we have increased concentrations in this polypropylene injection molding where we have a polishing and process adjustment processes. And then it collects or measures this signal in two different stages. And from those stages we can define the particle diameter. So it gives also like estimate for this diameter. And then from this diameter and surface area concentration we can derive also particle number concentrations. So these three units I will show in this each scenario. And here, for example, in this case, during this injection molding, we measured this kind of lung deposit surface area concentrations varying up to 50 micro square meters per cubic centimeter. And these are quite typical levels that are measured also in European cities. So these are not kind of high concentrations. And these are the particles which we collected from the work area. And the other case was tungsten carbide cobalt fine powder production. And we had two different processes. This powder was sieved and it was produced using these high energy ball mills. And here we also measured, like on the process side, the worker is applying powder from this feed funnel here. And here are the mills, so the worker is entering here in the milling room and taking the milled powder and putting the new ingredients in and so on. So, and in this case, the lung deposit surface area concentrations were quite low compared to previous one. And the particles, well, they were consisting of these kind of large fragments of tungsten carbide cobalt, and also other particles were present. And then this is handling of nanodiamonds. So here we measured concentrations from breathing zone and also from kind of near field. And we used other instruments also to measure. So we detected that, or we identified that these nanodiamond concentrations are here in large particle size range. So here is 1 micrometer and here is 10. And the microscopy samples also show that yes, these are like large fluffy agglomerates consisting of 6 nanometer like diamonds. And the concentration levels are there. I will summarize these later on, so don't worry. And in this fish lure manufacturing, they were having many processes in different areas, and the ventilation was so that the concentrations were pretty much mixed in all areas. So it was like a complex mixture of all kind of particles. And this was, by the way, in Finland, in rural area. And and here you see that these concentrations are in general very low. We have pigment particles and so on. But here in this polyurethane molding, we found that this is releasing lots of ultrafine particles, like up to 200,000 particles per cc. Yes, and this polyurethane, it includes also this isocyanide, so this is the most critical exposure part in this case. But and the last case is here in Denmark. They have this F-16 jet engine test site where Ismo and Eska was measuring concentrations using, again, disc minis and LPs and so on. And this is not kind of a relevant exposure scenario because workers are not allowed to go in this area when the jet engine is on. But of course these concentrations are exhausted outdoors and then diluted, and then these people are exposed to diluted concentrations. Here the concentrations were really high, also in particle number concentration wise, so here are millions of particles per cc, when typical indoor concentrations are some couple thousand particles per cc, and outdoor concentrations can be up to 100,000 particles per cc. So these are really high. And when we look now concentrations in these different workplaces and exposure scenarios, we find that these are low or in the same range as the concentration levels in some of the European cities. And in this jet engine emissions, we are in totally different magnitudes. So then we use this lung deposit surface area concentration to predict or calculate this deposited surface area in lungs during inhalation or during this 8-hour exposure. And this was just simply calculated by multiplying the concentration with the total inhaled volume. And then we divided it with lung mass, so we get this doses normalized with human lung mass. And then we can compare these with the toxicological studies considering these dose responses. So this was also published just recently, so we decided that okay, let's compare these levels with these dose responses, considering polymorphonuclear neutrophilia, which is indication of or strong indication of pulmonary inflammation. So in healthy lungs, we don't have these polymorphonuclear neutrophils. So the base level here is 0, and when it's increased, then it's an indication of lung inflammation. So the observable no effect level should be 0, and then this review study was made for low solubility, low toxicity particles like these, and transition metal oxides. And these are rat and mice experiments. So here they divide the surface area dose, which was instilled in the lungs, with the rat or mice lung mass. And then when we compare our dose values with these toxicological or dose responses assessed using animal studies, we can see that first the no-EL levels we have to divide with a factor of 10. So we take into account these intraspecies differences, and then factor of 10 so that we take into account the extra species factors. So we end up in these no-EL 100th levels for low toxicity, low solubility particles and transition metal oxides. And now we can make some sort of a scale which can tell that when we can consider that the work or the exposure level is safe considering this lung inflammation, and when we should start to pay more attention on the exposure, and when we are really like at the high levels and we should do something. This is clearly like, okay, the concentrations are already really high here. Like this is the jet engine emissions, so this is clearly something that yes, please wear respirators and protect yourself. And the other cases, these are like considered low toxicity, low solubility particles. So these are here clearly below the no-EL 100 level. And then these tungsten carbide cobalt particles are considered as transition metal oxides. And here we are now quite close to the no-EL 100 level. So maybe we should do some extra studies or pay more attention also. So this is a very new approach in a way, and there are many uncertainties related to exposure assessment, dose assessment, and of course dose response assessment. And here I have highlighted like the most critical parts, and as you can see, we don't know most of the things, and the uncertainties can be really high, like tenfold or so. And as a conclusion, I think this can be very useful monitor in future for this kind of in situ preliminary risk assessment. And we need more studies related to dose responses and also the exposure concept, this lung deposit surface area versus BET surface area, which is used in toxicological studies. And then there are other things which we have to take into account as well. So maybe in future we will have a new exposure level concept for airborne particulate matter, which is this LDSA. And if we look future prospects, so we know Ulla presented this nicely. in NIVA course some weeks ago. So it is known that particles induces these inflammatory and acute phase responses, and these are causing proteins in blood circulation, and these are causing further plaque formation in blood vessels, and this is leading to coronary heart diseases. So they have shown that these SAR3 levels are related to this acute phase response, and this is as a function of surface area dose. So it predicts this acute phase response, and acute phase response further predicts this coronary heart diseases. So, thank you. That was all reference.